In this lesson, we are going to define or to have a look at some of the basic concepts on phase transformations. Phase transformations are very important in many kind of materials. I would say in any kind of material, because in many cases the properties of the different phases are completely different, and so it's quite important to know what we have. The four questions we are going to ask ourselves during this lesson are: what are phase and the phase transformation? Why do we have any interest of them? What are the equilibrium conditions? And are they universal? Let's begin with the question: why do we have any interest on them? Let's do that with an example. We are designing an electromechanical device. It's supposed to operate at temperatures maximum 200 degrees, and then we use a solder for joining the pieces of copper, for instance. We use a solder which is an alloy of a composition 60% lead, 40% tin. This is a quite normal composition for solder. Melting temperatures of lead are 327 and for tin 232. We want our device to operate maximum 200 degrees. So in principle, we think, okay, we are below the melting temperature, so it shouldn't, of both components, so it shouldn't be any problem, because we are not going to pass over this melting temperature. However, when we go with our device to operation, the solder is melting and the pieces of the device fall apart, and we don't understand why. Why does it happen? That's why this is the in principle, don't worry about. We'll come back later to this kind of diagrams. But what we see here is here we are representing the composition of the alloy. Here we have pure lead. Here we have pure tin, and here in between we have a certain composition of tin. And here we are representing temperature. And in this diagram, what we see is that at high temperature, we have a liquid which is formed by tin and lead. At low temperature, we have here a solid, or here another a different solid. And here we have two solids which are coexisting, which are present simultaneously. Then the composition of our solder is here. Here is our solder composition, which is 40% tin. And what we see is 183. What happens is that the material, if we are heating up at 183, the material melts. So that was the problem. Why? Because here we have a phase transformation, because here we have two different phases for this material, and here we have the coexistence of both, and we have different kind of phase transformations here. Then it's important to study what is happening there. Yeah? Second question, are they universal? Because I have just shown an example in which I have an alloy lead tin, and are this kind of phenomenon universal? Of course, you know already that they are, but how universal? I present here three indeed very different examples. One is a diagram of milk, a quantum dot, and water. Let's go in detail in some of these, in any of these diagrams. This is the diagram from milk, and this is the diagram, the phase distribution, the important temperatures when I'm trying to go from milk to powdered milk. If I want to dry the milk to get powdered milk, that afterwards I can rehydrate to have again milk, then it's that's what I find. Then represented here is first temperature here in this axis, and here total amount of solids. Milk is water and sort of a lot of proteins that are dissolved in this water, and these are visible that could be solids. Okay. two phase transformation. First one at high temperature, which is above 93 degrees in principle. Then nucleation of an alpha hydrate lactose crystal in a supersaturated milk concentrate is occurring. Yeah. Second, at much lower temperature, we have the nucleation of the beta anhydrous crystals in a very glassy powder state. So you see, this phase and this phase are completely different. That means that if I come in the drying process through this path or through this path, I'm going to get a completely different compound, a completely different quality for this powder milk. At the end of the day, it will be powder milk, but has nothing to do in the cases, in the composition I have. Okay. Another example is quantum dot. Quantum dot, you see, is like a dot in which I have a high degree of confinement of the carriers. Normally, they are made by the position of the compound I want to grow for the quantum dot on a substrate. There are different types of growth for thin layers, for dots, for whatever, which are represented here. Then we have the Vollmer-Weber, which is island formation. Then I have my substrate, and as as I'm increasing the amount of material deposited, then I'm forming island that grow. Yeah. Then I have another possibility, which is the Frank van der Merwe. In this case, the growth occurs layer by layer. I mean, there is no island, but at first you see it's a layer. When this layer is complete, another layer is begin to grow. Then I have two layers, and here on top of, I will have another another layer, if I go on with the growing. And finally, I have a mixed mechanism, which is the Stransky-Krastanov, in which I have first a layer, and once I have the first layer, first couple of layers, then islands are beginning to form. So I have the layer here, and then some islands begin to appear. If I go to the diagram, to the phase diagrams that I have, is here. This material is the highest value of the surface energy. In this case, I have a system in which I have the lowest gamma value, so the lowest value for the surface energy. For these two, I leave the question open. But what do we have here? What we have here is, here I'm representing coverage, so how many, the degree of coverage of the substrate, and here I'm representing misfit. So if I have a substrate here and a different material here, of course this material in the substrate and the material I'm depositing are not the same, and so a certain degree of misfit between the lattices of both materials is going to occur. Okay, then here coverage, here misfit. What I see is that first, for instance, in this case, where I have the highest value for the surface energy, FM process occurs, so Frank van der Merwe, layer by layer. It's normal because the surface energy is too high. And as far as the misfit increases between in the system, then change to other system. Here we have ripening, which is the coalescence of the different layers that are growing. And here I have the Vollmer-Weber. In this case, I have Frank van der Merwe, Vollmer-Weber, Stransky-Krastanov, another type of Stransky-Krastanov, another configuration of island, and finally ripening for high coverage degrees. And here I have the same Frank van der Merwe, Stransky-Krastanov in these two different processes, Vollmer-Weber, and then ripening at high coverages. And the same here, but here I don't have the Frank van der Merwe since the surface energy is very low. Yeah? So it's very important if I want to know how it's going to grow my quantum dot, my material. I must now in which conditions I'm going to have good crystals, good films, etc. A diagram you know quite well. This is the water diagram, and you will surely you are recognizing this part of the diagram. This is the triple point. So here you have ice, vapor, liquid, and surely you recognize here the critical point you have studied in thermodynamics. Let's go in a little bit more detail in this diagram. You can also suspect here something. I have many labels written here. These are all the different types of ice. How is these different types of ice? Let's go. You have here all the different phases. You see that the crystal, the crystalline group, the symmetry group is different for any of these phases, all the phases that are represented here. Probably you will see it better here because then you have the liquid as the most useful, usual form, which is to the right, and here we are representing pressure, and here we are representing temperature, and these are all the different phases of ice that can occur at different temperatures and pressures. See that here are gigapascals. So now we have answered to these two questions. Why do we have any interest on them? Our device was broken, and are they universal? At least we have seen three completely different systems, four with the alloy, in which we have phase transformation that are quite important, so we can assume that they are universal. Then, what are phase and phase transformation? Three important concepts in the phase transformation are phase transformation itself, and microstructure. Phase is homogeneous physically and chemically, I mean from both points of view, from composition and from structure and properties. It's a homogeneous portion of a system in material. It's as you know, and you have done in thermodynamics, it's characterized by thermodynamic variables that allow you to specify in which state the system is. The thermodynamic parameters, if you have all the thermodynamic parameters of the complete system, then you can have a lot of information from them, and on the other hand, you can get all the information to have these parameters from those of the constituent system, or the constituent phases. When the system or material change from one phase to another, of course, we talk about the phase transformation. And the microstructure, in this case, refer to the number of phases present, the proportion, their distribution within the system, their composition, and of course, it depends on the number of components, on the concentration of each of the components, and in many cases, in the thermal history of the system. You have here some examples. Here, water, for instance. I have three phases here: water, ice, water vapor. Also, I have here solution, water, alcohol, solution. Here I have three different phases. Here I have only one phase. Here you have water and salt. If you are below the solubility limit, you have only one phase. If you go over the solubility limit, then you have two phases. One is this brine, which is saturated here, and then all the excess salt that is deposited on the bottom of the vessel. And here also you have two phases. One is water, and that's soil. Because here you have two separated phases, which are completely different. You can distinguish perfectly. Here you could only distinguish one, and here you could distinguish two. One and 1, 2, 3. Yeah, that's the phases. Next question: what are the equilibrium conditions? The concept of equilibrium is I'm not going to go into detail. It's absolutely essential in all physical and chemical processes, and macroscopically, the equilibrium condition, or to say that we're in equilibrium, translates into system characteristics that do not vary over time. In particular, they do not vary over time regarding microstructure and then composition, phases present, etc. Okay. The way to represent the equilibrium conditions is the phase diagram. It's a way to represent the relations among composition, proportion, structure, temperature, whatever. It depends on the system. We've seen already several examples. Here you have an example in which you have temperature, composition, sugar, and water. Here I have no sugar. Here it's also, only sugar, no water. Then I have here a liquid solution, a syrup, more or less sweet, more or less sugar inside. And here I have a liquid solution, like with the salt and the salt brine. I have a liquid solution and some solid sugar that has deposited, that have been precipitated. And here, in this boundary, we have the solubility limit. At the point I cannot, at this temperature, I can dissolve more and more and more and more sugar till I reach this point. When I reach this point, I'm not able to dissolve more sugar in the water unless I rise the temperature. Okay? So, important phases present are the temperature and composition, proportion and composition of each phase, temperatures at which transition occurs, and solubility. And as told, if I come here, then I see 60 degrees, for instance, then I come here, I'm increasing the amount of sugar, more sugar, more sugar, more sugar, more sugar. Puff, I reach here the limit. I cannot add more sugar without going to this state in which I have solid sugar precipitated. Okay, and that's why if I want to test the coffee with ice, I must put the sugar before the ice, and not on the opposite. That's you now, but let's remind some of the thermodynamic potentials. So here we have the heat capacity, which is the derivative of the enthalpy of temperature. Here we have enthalpy, and here we have entropy. Yeah. Usually, when we handle equilibrium systems or equilibrium states, we are more interested on the Gibbs potential. The Gibbs potential, which is the free energy, is the enthalpy minus temperature times entropy. That's represented here. Here you have the enthalpy. Here it's the here's the enthalpy. Here's the free energy, and here's the difference temperature times entropy. And of course, if you consider the slopes, then the slope of the enthalpy is here is heat capacity, and the slope of the Gibbs function is minus entropy. In the phase transition, what happened? For instance, let's consider one simple phase transition, which is from solid to liquid. What happened is, okay, I have the liquid, this is the enthalpy, this is the Gibbs function, and in the solid, this is the enthalpy, this is the Gibbs function. As you know, at the melting point, at the point in which the transition phase occurs, there's something we know is latent heat. So, you know, if I am heating a piece of ice, for instance, I'm heating a piece of ice, I'm giving some heat, some energy to the material, to the block of ice, and then the temperature is rising, rising, rising. When I reach the melting point, then temperature stabilizes. Even if I give more and more heat to the material, to this block of ice, temperature does not change. It's just going to be stable at 0 degrees. And then what happens is that the ice begins to melt. And then I have ice and water, ice and water, ice and water. And when finally all the ice has been melted, and then I have only water, if I still go on heating the system, then the temperature will rise again. Okay? So this is the latent heat. This is the heat which intervene with the heat which is involved in the transformation, the phase transformation. Then let's go for the Gibbs function. Then at the high temperature, you see in equilibrium, you know that the Gibbs must be a minimum. At high temperature, liquid is below solid, so liquid phase is stable. At low temperature, solid here is below liquid, then solid phase is stable. We have all the questions we have already answered. So see, it's written here. Phase 1 is stable, phase 2 is stable. Now we are not talking about liquid and solid, but phase 1 and phase 2, but it's the same condition. And at the temperature which is equal to the transition temperature, both Gibbs energies are equal, so both phases are stable. That is. However, it seems that when the phase change occurs, it seems that a decrease in the free energy must occur. Or, better to say, a phase change is only going to occur if, as a consequence of the change, a decrease in the free energy occurs. For instance, here we'll change from solid to liquid, or phase 1 to phase 2, phase 2 to phase 1 in this case, because there's a difference in the free energy, phase 1 or phase 2 and phase 1. So, but then both are equally stable. And so that means at the equilibrium position, at the equilibrium point, the driving force is 0. Then does the change occur at all? Of course, you know, obviously it does, you know, but that will be a topic for next chapter.